right, so today we're going to be talking about transformations from section 1-6. And the reason why I didn't include this in with the batch of the rest of the review material that was on the first quiz and those first 5 sections is because we do have some notation that is different from the way you were used to seeing transformations in Algebra 2. So I just want to make sure I cover some of that. So first thing, if you look at your text, this is table 1.4, but it's in section 1-6 with the transformations. Here are all of the parent functions that you are going to be expected to be able to transform. So these are all types of functions that you learned in Algebra 2, and these are the ones that we're looking at right now. We'll review other functions later, but for right now, this is what we've got. Our constant function, which are, originally horizontal lines. Then we've got the identity function, which are, lines that have an actual x and not just a number. Absolute values, parabolas, which come from quadratic functions, square roots, cubics, cube roots. So I just wanted to draw your attention to this. Obviously, you can see this in your text at any time, but just wanted to point it out that it's there for you if you feel like you need to review those parent functions. And then in table 1.5, they've got a summary of the transformations. So everything that is in here is what you learned in Algebra 2, except for in Algebra 2, we did not discuss reflection about the y-axis, which is what happens when you replace x with the opposite of x. Here, reflection in the x-axis we did do, and that's when the negative is out in front, meaning that you're multiplying the y by -1. Now, the notation here is a little bit different. Here, when we're adding values on the outside, back in Algebra 2, we wrote these equations, let's say I was doing an absolute value, we would have like the A, absolute value, B times X minus H, and then plus K. So this is just a different type of notation. They are saying, okay, if the C is on the outside, which would be like the K value, those are my vertical shifts. When the C value is on the inside, so in this case, inside the absolute value and it's added or subtracted, that's a horizontal shift. We already talked about the reflections. Vertical shrink and stretch and horizontal shrink and stretch. We had both of these in Algebra 2 as well. In the middle, it tells you like what you would do to the y coordinates or x coordinates, depending on which type of transformation we're talking about. But again, notice that on vertical, it's multiplied on the outside. On horizontal, it's multiplied on the inside. So we're going to do some more work with this momentarily, but I just wanted to kind of briefly show you this valuable resource that's in your text as well, in case you want to use that for your studying. I also here then am going to draw your attention to the packet that you have. So we are going to do just a little bit of this packet together, and then the rest you'll finish up yourself. I'm going to go ahead and skip over to the reflections, because since one of the types of reflections is new for you guys, I figure that's a good way to start. And then what you see me do on this page, you then will be doing similar things on the first 2 pages and the next 2 pages. So with reflections, it tells you can use your graphing calculator. Because you've had these functions in Algebra 2, you really might be able to do it without a graphing calculator. But if you can't, certainly feel free to go ahead and use it. So in this case, we have the negative times the square root of x. So I'm going to go ahead and pretend like you don't remember what's going on from Algebra 2 just to fully illustrate. So I'm going to type in the opposite of the square root of x as my function, and I have no idea what type of window I have, so I'm going to go ahead and zoom 6. And here we see the graph of that function. I called the square root functions the eyebrow functions because that's what they kind of look like. In this case, it's been reflected over the x-axis. It does ask me for the values when x is 0, 1, and 4. Now that you can either get by just simply plugging it in, so the opposite of the square root of 0, which would be 0. Then you've got the opposite of the square root of 1, which would be negative 1. And then the opposite of the square root of 4, since square root of 4 is 2, that would give me negative 2 there. So I can certainly just kind of do that by hand and plot my 0, 0, 1, negative 1, and then 4, negative 2, and then connect those with my lovely eyebrow shape. Or you can go to your calculator and remember that if you do second graph, that'll show you the table. Notice there's error before that, but 0, 0, 1, negative 1, and then you'd skip down to the 4, negative 2. So you can get those points either way. So then it says if g of x equals the opposite of f of x, then g of x is a transformation where f of x has been. It's asking you to describe what's happened. So regular square root of x, if I graph that in black, would have been here. This is the parent graph. And so all we've done here, it has been reflected in the x-axis. If we know points on f of x, we can find points on g of x by, this is describing what we would do to get the actual points themselves. So instead of 1, 1, I have 1, negative 1. Instead of 4, 2, I have 4, negative 2. So what we would say here is what the changes are to the actual points. So when you do this, you describe which coordinate and what you do to it. So in this case, we would say by multiplying the y coordinates by negative 1. And that's what we would have there. So we've described the name of the transformation, meaning what's happened when I look at the graph, and how would I get the actual points from the original. So then to finish out the page here, use your graphing calculator to graph g of x equals the square root of negative x. So again, totally up to you. You can either do this by hand or use the calculator. Since I showed you the calculator on the last one, this one I'm just going to do by hand. So if I plug in negative 4 for x, I just want to illustrate this. This is what I'm getting. The opposite of negative 4, or negative 1 times negative 4, which is just the square root of 4. So this gives me 2. Opposite of negative 1 is 1, square root of that is 1. The opposite of 0 is still 0, and the square root of 0 is itself. So I would plot negative 4, 2, negative 1, 1, 0, 0. So it's still making the eyebrow shape, but it's going this way. If I compare that to the parent square root graph, which again was the dashed one in black here, what has happened when I'm talking about description of the graph is that, and this is a typo, sorry, copied and pasted and didn't actually fix it. This would be f of the opposite of x, because that's what we did here. We replaced what was a normal x in the parent graph with the opposite of x. Then g of x is the transformation where f of x has been reflected in the y-axis this time. If we know points on f of x, we can find points on g of x. So if we were to look at points on f of x, 0, 0, 1, 1, 4, 2, we can see that it's the x coordinates that have changed and they've become negative, which means we would say we can find g of x points by, and you can either say multiplying or dividing the x coordinates by -1. In this case, it doesn't matter because multiplying or dividing by -1 give you the same result. So we would say x coordinates by -1. So hopefully that makes sense, and that kind of gives you a start. The next thing I want to look at is the new notation that you're going to see. So if you skip over to the page where it says up at the top, it's near the back of your packet. I think it's the second to last page of the packet. It says overview of putting all the transformations together to find corresponding points. Suppose f of x is a function. Now what we're graphing is this. Notice that I've used some of the same letters that you're accustomed to from Algebra 2. What we have here is a times the function, and then on the inside we've got b times x plus h plus k. Now here's the difference. In Algebra 2, we would have written it like this. First of all, we would have used lowercase, and we would not have used the F notation, but we're going to continue to use that this time. So we'd write A times F of, and then we would have had it written like this. So the big difference between the notation you're going to see in this text and throughout pre-calc and probably into calculus as well is that they don't have the b term factored out. And that makes a difference when we are talking about what we're going to do with the values. So you are more than welcome to use your knowledge from Algebra 2. And if it's easier for you to just factor the b out, which would change this h value, and do it with those transformations, you can. The other way that we can do it is by following this kind of order of operations. And that would be that we always, when we have these transformations and this format, is that we use this order. We start with the h and we subtract that value from the x coordinates. So if this says plus 3 right here, so plus h, I would subtract 3 from all the x coordinates. Then divide the x coordinates by whatever b is. Then multiply the y coordinates by a, and then finally add k to the y coordinates. So these are kind of point-to-point transformations as opposed to a transformation thinking of the entirety of the parent graph. So I'm going to do number 2 here just to illustrate this, and then we'll do a couple more examples to kind of make sure you have a good start to know what you're doing. So suppose f of x is transformed so that g of x equals the opposite of f of 2x with a -3 on the outside. If negative 5, 6 is a point on f of x, find the corresponding point on g of x. So this one, I would suggest using point to point because it's not a parent graph. It's just an individual ordered pair. So if you know this, which obviously you'll have to make sure you do know this order, it tells us to start with an h. Well, h would be on the inside of the parentheses and it would be added or subtracted. But there isn't anything here. So that means I get to skip step 1. So step 2, divide the x coordinates by whatever b is. B is a multiplied number on the inside of the parentheses. In this case, 2. So that means the first thing I'm going to do is I'm going to divide the x coordinates by 2. So the x coordinate is negative 5. When I do that, I get negative 5 halves. Do not use decimals. Remember, unless there's a decimal in the original problem, or the directions tell you to, or it's a real life situation. Notice it did not say to change the y coordinate right now. So that's staying. So I did that. Now I look, multiply the y coordinates in step 2. So take this answer, not the original, multiply the y coordinates by a. So multiply y coordinate, a in this case is negative 1, so by negative 1. So my y coordinate is 6. When I multiply that by negative 1, that gives me negative 6. Then finally, add k to the y coordinates from step 3. So, meaning, again, take this answer. We're not starting over. And so I'm going to add negative 3 to the y coordinate. Now, adding negative 3 is the same as subtracting 3, so totally fine with me if you say subtract 3 from the y coordinate. So x coordinate stays the same, negative 6 minus 3 gives me negative 9. This would be my final answer. This would be what I get when I complete the transformations. I would suggest learning this and using it anytime what you're given are individual points. If what you're given is a parent graph, then I probably would revert back to, just knowing what the parent looks like and performing, those transformations. If you look, the back of your packet, this is not a parent graph. It's a whole bunch of individual points. So I would suggest just writing down like the original points here and then just showing what you get after each step. I think there are more spaces for steps than you really need there, but that would be my suggestion so that then you can plot it. There are some of you who, even though this isn't a parent graph, some of you are going to be able to look at that and just perform all the transformations at once just by knowing, okay, this means a vertical stretch by a factor of 2. This means I'm going to move it this way and that way. If you can do that without filling out the table, totally fine with me. I am not one of those people. I have to fill out this table when it's not a parent graph. But if you can, that's awesome for you, and go ahead and do that by all means. All right, last examples that I want to go through are some examples from some of the exercises here in the book. So let me flip back over to that. And so if you go in your exercises to the graph that's right above number 17, that's what we're going to be doing. And we're not doing all of these here. I'm just going to pick out a few to just kind of illustrate how you could either do it by looking at the original graph, or you could do point-to-point transformations. So I just want to make sure you understand that you have a choice on these and you can choose whatever makes the most sense to you. So we're going to start with number 22 right here. And I'm going to color code everything so that way you can, because we're going to have lots of different points on this graph up here. So according to this right here, I have an added value on the inside and a subtracted value on the outside, which that means I have an h and a k value. And so with what you learned in Algebra 2, you would look at this and you would say, okay, a plus on the inside means I'm going to move to the left. So this is a horizontal shift, left 1, and then this minus 2 on the outside is a vertical shift, down 2. So because this graph is made up of a bunch of individual points, you could do the point-to-point transformation, or you could just use this and say, okay, I know I need to go left 1 and down 2 for all of these. So take this point, left 1, down 2. This point, left 1, down 2, left 1, down 2, left 1, down 2, and the last time right here, and then connect them. Oh, sorry, sometimes it's hard to connect using this software and pen, so sorry that that looks like a curve. It should be a segment. So you can do it that way, or you can look at it and say in order, okay, I'm going to list these 4 points, and for each of those 4 points, so let's say I have -4, 0, -2, -2, 0, 0, 2, 2, and 4, 0. And then you could say, all right, subtract h. So subtract 1 from all the x coordinates. So x coordinates, -5, 0, -3, -2, -1, 0, 1, 2, 3, 0. Then you would go to the second thing. I don't have a b value, so I can skip that. I also don't have an a value, so I can skip that. Then it says add k to the y coordinates. So my k is -2, so that would mean take all these y coordinates from this step right here and add -2, which would mean subtract 2. And so if I do that, then these are the points I would end up with. Notice that they're the exact same points I got from doing it this way. So I just want you to realize that you have multiple options there. All right, let's look at another one. Let's look at number 25. And I'll switch my color again here. So having the -x instead of x means that I'm going to have a reflection in the y-axis. And this +1 means that I'm going to have a vertical shift up 1. So again, some of you are going to be able to do that just by looking at it. So you can say, okay, if I shift this up 1 and I reflect it over the y-axis, it ends up on top of itself. This guy right here, I shift it up 1, then I reflect it over the y-axis, and it ends up here. This point, shift it up 1, reflect it over the y-axis, it goes here. This point, up 1, over the y-axis. And finally, this point right here, shift it up 1, then reflect it over the y-axis, and in green, a little better job connecting it this time, would be that transformation. So there I just did it visually. If I wanted to, I could go ahead, and what this would be is this is a b value of -1. This is a k value of 1. So in the orders, the b value, we would divide the x coordinates by b. So I'm not going to rewrite the originals because all the originals are the same. But I would divide all the y coordinates or sorry, divide the x coordinates by -1. So that'd give me 4, 0, 2, -2, 0, 0, -2, 2, and -4, 0. And then I would, because I have a k value, add k to the y coordinates from here. So 4, 1, 2, -1, 0, 1, -2, 3, and -4, 1. And again, you can see that these answers match what I plotted in green. All right, final illustration, and hopefully that'll be enough where you feel like you can finish. I want to look at number 30, which number 30, I have f of 1/2 x. The reason why I wanted to do this one is because this is a b value that's a fraction. So if we are looking at just the graph itself, what we have here is a horizontal stretch by a factor of 2. Because remember that you learned in Algebra 2 that the factor of the stretch is the reciprocal of the b value. So if you can stretch this into 2 times as long visually, go ahead and do that. I can do these first two visually. I have lots of problems when it comes to shrinking and stretching visually. So this one, I actually would prefer to use the b value. So the b value here is 1/2, and according to our overview, b values, we divide the x coordinates. So dividing by 1/2 is the same as multiplying by 2. So what I would really be doing here is I would be taking those values and multiplying them by 2. So I would then get -8, 0, -4, -2, 0, 0, 4, 2, and 8, 0. So 6, 7, 8. Here's where 8, 0 would go. Then I'd have 4, 2 right up here. 0, 0 still on the origin. I'd have -4, 2, and then -6, -7, -8 right about here. And once you plot it, oops, I plotted somebody wrong. Oops, it's this one. I'm glad it wasn't the one that I connected already. So forget that point. That's not supposed to be there. I lied. It's the other one. So let me adjust the color here. I'm going to put this in. Let's see, what color have I not used at all? Let's try a purple, perhaps. Sorry, because it was this point I plotted wrong. That's supposed to be -4, -2. So in purple would be what that graph should actually look like, not the blue. So once you see it, you can see, oh, look, if I compare the original, it's twice as far on the horizontal scale. So again, if you can do that visually by just writing this and then plotting it, that's great. I usually need to rely on the points once I start having fractions and all that kind of stuff. All right, so your practice then is to go ahead and finish up the remainder of that packet following the examples that we did.